Imagine this. In a futuristic laboratory, a team of scientists activates a device that compresses matter to extreme limits. And in an instant, out of nowhere, a tiny black hole appears. It starts devouring everything around it, and the scientists realize with growing horror that they can't stop it. Sounds like science fiction, right? But today we're diving deep into the science behind black holes to find out if humanity could technically create one, what conditions would be necessary, and what would happen if an experiment like this spiraled out of control. Ready to step into the abyss of science? Then let's go. Let's start with the definition. What exactly is a black hole? A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from it. It forms when a massive star collapses under its own gravity. Key characteristics of a black hole: event horizon, the boundary beyond which nothing can escape; singularity, a point of infinite density at the center; Hawking radiation, a theoretical process through which black holes can evaporate. Black holes come in different types: primordial, hypothetical microscopic black holes; stellar mass, formed from collapsing stars; supermassive, found at the centers of galaxies. If the Earth were compressed into a black hole, it would be the size of a pea. So let's find out. Can humanity technically create a black hole? At the current stage of scientific and technological development, humanity does not have the capability to create a black hole. Black holes naturally form during catastrophic cosmic events, such as the collapse of massive stars, and they have gravitational fields so strong that even light cannot escape. To technically create a black hole, matter would need to be compressed to an extremely high density, a process known as gravitational collapse. This would require an enormous amount of energy, technology that does not yet exist, and a controlled environment, which is also beyond our reach. However, some laboratory experiments are approaching the creation of miniature objects that resemble black holes, such as in studies involving the Large Hadron Collider. But these remain theoretical concepts that are still far from reality. There are several theoretical models of mini black holes being studied by scientists. Non-singular black holes. These models avoid the singularity, which is a mathematical problem in standard black holes. For example, the Hayward metric describes a regular black hole that does not have a singularity. Mini black holes created in laboratories. Some theories suggest that mini black holes could form at extremely high energies, such as in the Large Hadron Collider. This idea is based on the possibility that, at sufficiently high energy levels, particles could create an extremely dense object. Quantum black holes. In the framework of quantum gravity, it is predicted that black holes could be very small, yet stable due to quantum effects. Ion Beato Garcia models. This is the first exact model of a charged regular black hole, incorporating nonlinear electrodynamics. These models remain theoretical and require further research to confirm their reality. What would happen if one appeared? If a black hole, even a small one, were to appear in our surroundings, its impact would be significant due to the immense gravitational field it generates. Even a tiny black hole could attract surrounding matter, including gas, dust, and other objects. If it were near Earth, it could cause catastrophic changes by disrupting everything in its path. According to Hawking's theory, many black holes emit energy and gradually evaporate. However, even the smallest black holes could exist long enough to affect their surroundings before disappearing. If a mini black hole were close enough, it could consume parts of Earth's material, possibly even its core. This would lead to significant destruction and potentially alter Earth's orbit. If a larger black hole were to suddenly appear near Earth, the consequences would be far more dramatic and catastrophic compared to a mini black hole. A massive black hole would warp space and time on a much larger scale. Its gravitational pull would disrupt the orbits of nearby planets, moons, and asteroids, potentially causing chaos in the entire solar system. As objects, including Earth, approach the black hole, they would experience extreme tidal forces, stretching them apart in a process often referred to as spaghettification. This would lead to the complete disintegration of anything caught in its influence. Matter from surrounding celestial bodies, including gas, dust, and even stars could form an accretion disk around the black hole. As this material spirals inward, it heats up to incredible temperatures, emitting intense radiation that could be deadly for life on nearby planets. If the black hole were close enough to Earth, it would likely strip away the atmosphere and oceans, making the planet uninhabitable. The sheer energy output from the black hole could also expose Earth to lethal levels of radiation. In a worst-case scenario, Earth itself could be pulled into the black hole and completely destroyed. Now let's talk about Hawking radiation, how it actually works, and could a microscopic black hole actually survive? Hawking radiation is a theoretical phenomenon proposed by Stephen Hawking in 1974, which explains how black holes can lose mass and energy, gradually evaporating. It is a process based on quantum mechanics. In the vacuum surrounding a black hole, pairs of particle-antiparticle are constantly forming due to quantum effects. Normally, these particles annihilate each other almost instantly. If a particle-antiparticle pair forms near the event horizon of a black hole, one particle may fall into the black hole while the other escapes into space. The black hole loses energy and thus mass to compensate for the escape of the particle. This appears as radiation emanating from the black hole. Over time, the black hole loses more and more mass due to this radiation, eventually disappearing completely. Microscopic black holes have very small masses, so the Hawking radiation would be much more intense compared to larger black holes. As a result, such black holes would evaporate extremely quickly, in fractions of a second. However, if they were formed in the early moments after the Big Bang, they might have had enough mass to survive until now, though this remains purely theoretical. But what if the black hole was the size of an orange? Could we control it? A black hole the size of an orange may sound tiny, but its mass and gravitational pull would be anything but manageable. Even a black hole that small would possess an immense amount of mass, likely equivalent to that of our planet or even greater, compressed into a space the size of a fruit. The black hole's gravitational pull would be so strong that controlling or containing it with any known technology would be impossible. Any object or matter brought near it would inevitably be drawn in. If such a black hole appeared on Earth, it would begin consuming nearby matter almost instantly, including air, ground, and anything else in its vicinity. This process would cause catastrophic damage within moments. Theoretically, an orange-sized black hole might emit Hawking radiation we talked about, causing it to lose mass over time. However, the rate of radiation would depend on its mass, and for a black hole that size, it would likely persist for a long time, potentially causing prolonged devastation. Human control over a black hole of any size is well beyond our current understanding of physics and engineering. Even theoretical exotic matter or speculative technologies, like those proposed in science fiction, wouldn't suffice to contain or manipulate such an object. So an orange-sized black hole would be far from something humanity could control. It would be more like an unstoppable force of nature. That said, the formation of such a black hole near Earth is extraordinarily unlikely under natural circumstances. Could black holes be used for energy generation or as an interstellar engine? Theoretically, yes. Black holes could be harnessed for energy generation or even as interstellar engines, though such ideas are purely in the realm of speculation and science fiction at this point. Black holes could potentially serve as a massive source of energy via methods like Hawking radiation. As black holes evaporate through Hawking radiation, they release enormous amounts of energy. If we could somehow harvest this radiation, it could provide a nearly limitless energy source. However, capturing and controlling this energy presents immense technological challenges. Accretion disks. The material spiraling into a black hole forms an accretion disk that gets incredibly hot and emits high-energy radiation, particularly X-rays. Capturing this energy could, in theory, generate power. Penrose process. This concept involves extracting energy from the rotational energy of a spinning black hole, Kerr black hole. By sending matter into the black hole's ergosphere at the right trajectory, some of the black hole's rotational energy could theoretically be harnessed. The idea of using a black hole as a propulsion system has been proposed in various hypothetical designs. Black hole drive. In this concept, a small artificial black hole could serve as a high-efficiency engine. By directing the radiation emitted from the black hole, a spacecraft could achieve propulsion. The energy density of black holes would allow for immense thrust, enabling interstellar travel. Photon propulsion via Hawking radiation. The Hawking radiation emitted by a black hole could theoretically be funneled to create a photon drive, propelling a spacecraft. Controlled sling effects. Using the gravity of black holes to slingshot spacecraft at incredible speeds might help in long-distance interstellar travel. While these ideas are enticing, the technological barriers are staggering. Creating or capturing black holes safely. Developing materials and systems capable of withstanding extreme gravitational and radiative environments. And managing and redirecting the immense energy output. So, we can conclude that black holes are among the most fascinating and mysterious phenomena in the universe. They ignite the imagination with their unique properties, such as the gravitational force capable of consuming everything around them, and Hawking radiation, which allows them to gradually disappear. We explored the possibility of their creation, the potential consequences of their appearance, and the fantastic ideas of utilizing black holes for energy generation or space travel. While many of these ideas remain theoretical, they push humanity toward new discoveries in physics and astrophysics. Black holes symbolize how much of the universe remains unexplored, and studying them is key to understanding the fundamental laws of nature. Who knows, perhaps one day they will not only be a source of mysteries, but also a driving force for technological and scientific advancements. If you want some more interesting facts and crazy theories about space and our universe, subscribe to the channel and press the like button. Write in comments what you see in the next video. Goodbye, space lovers. Stay tuned.